We now look at a simple program that tries to identify the cache properties to see that these cache structure does in fact impact the practice. The main idea is to use the following two nested for loops. The first for loop runs from 0 to some big number divided by n, and the second for loop runs from 0 to n. And the second for loop accesses an array of size n. So in total, the total number of memory accesses is given by this number multiplied by this number. So n cancels out, so this means in total there are this many memory accesses. So if every memory access to memory takes exactly the same amount of time, then this algorithm should always run in the same time because the total number of memory accesses is fixed. The question is, are we going to see such fixed behavior in practice or not? So the first way to run this is to run it without optimization. Just take this program, compile it, and simply execute it. If you run it without any optimization, you'll see that the running time is pretty much constant, no matter how you change the value of n. This is because there are lots of instructions that are executed in a non-optimized compile of this code. This means for every memory access, the processor needs to execute many extra instructions. So that means that even if the memory access is a bit slow, that slowness is masked among all the other instructions that the processor needs to execute. However, if you optimize with the best possible optimization, the compiler using the O3 option or the level 3 optimization removes the code that does this. So there will be no memory accesses produced. Same thing happens if you cheekily try to just print the sum. Again, the compiler optimizes this because this array is not initialized. So the proper way to run this experiment is to allocate a memory of size n, initialize it, and then sum it up. In this way, the sum is in fact a meaningful entity, so the compiler cannot optimize and remove it. If you do this, then you might see a behavior that looks like this, if you use proper experimental setup. You'll see that for small values of n, the access time is fast, but as soon as n crosses a critical value, the access time shoots up. This is because for small values of n, the whole input will fit in the cache. So therefore, we'll have fast access to all the elements of the input array. But as soon as the input size grows beyond a certain cache size, the input does not fit. That means every time you need to look at an index of the array, you have to fetch it from the memory or from a level of the cache below it. So using these experiments, it was possible to detect that the size of the L1 cache is this much, the size of the L2 cache this much, and the size of the memory is roughly this much. Simply by looking at the positions where this access time jumps a little bit.